So I'm very happy that I got a wonderful chance to speak about some exciting topics. I mean about the physics of black holes. Back to my alma mater, PSMO, and to meet my beloved teachers. So first of all, I would like to thank Basim sir and Nizam sir and all the teachers of the department for setting up such a wonderful chance for interacting with the students. I understand that many of the students here they have just joined the department, and so this is a as I am a student who has completed 3 year undergrad course there, so I know that okay, this department is one of the best department in Kerala, such that this if you have that passion of doing physics, our department is there with full support, such that you can get all the heights that can be achievable for a student in physics. So with this preface, I think I would start the topic of discussion. So today I'll be discussing about the physics of black holes. So as we know, the 2020 award of Nobel Prize is given for astrophysics. So it is given to Roger Penrose. First half is given to Roger Penrose, and the other two half is divided between Rainer Genzel and Andrea Ghez. So if I read the Nobel statement, so this award is given for the discovery that black hole formation is a robust prediction of the general theory of relativity. And the other two contribution is the discovery of supermassive compact object at the center of our galaxy. So with this introduction, let me go to the outline of my talk. So briefly, I will start the talk with speaking about the Nobel Prizes given in astrophysics in general, and I will introduce something about the Newtonian physics and how we are going to general relativity, which gave us the wonderful predictions like the black holes. And I will briefly explain these black hole formation scenarios. How can we get these enigmatic stuffs like black holes? And I will, in the last part of the talk, I will give some glimpses of ideas related to the singularity theorem, which gave Nobel Prize to Roger Penrose, and what happened at the galactic center that gave Andrea Ghez and Reinhard Genzel the award. Then finally, I will shortly, if the time permits, I will explain some of the works that we have done on understanding the formation of supermassive black holes. So here is the brief history, like how the Nobel Prize is given in astrophysics. So we know that astrophysics is a very fascinating topic to every one of us. So that is reflected in the Nobel Awards also. So from 1967, this award is given. So this is today, I mean, this year's award is the 11th award. I'm not going to read the complete list here, but I just want to highlight some of the awards. So in 1978, discovery of CMB radiation was awarded, which was actually gave the observational proof that the cosmological starting was actually a big bang, and it was not a steady state. So this CMB radiation was awarded. And later, another very important one is this 1983, where the studies of the structure and evolution of stars. So it was actually won by Subramanya Chandrasekhar. He was an Indian origin physicist, and he got the award for predicting the famous Chandrasekhar limit. Then something interesting is the 2011 award. So 2011 award is to the supernova observations, which actually told us that universe is accelerating. So from the very early days, like when in 1929, Hubble has found that the our universe is expanding, the galaxies are moving away from us, but we haven't had any clue that whether the expansion was accelerating or whether it is decelerating. So up to that, gravity was the only force which we know. So we thought, okay, this is a decelerating universe because gravity is always attractive. But later we found that no, based on the supernova observation in 1998, Rees, Perlmutter, etc. So they found that okay, universe is accelerating. So this award was given. Then later, very recently in 2017, detection of gravitational waves by LIGO. So they also, the LIGO team also was given the Nobel Prize, the famous Kipton and runner base, etc. So I remember during this time, I was given again a wonderful opportunity to interact with the students in the department in 2017 to speak about gravitational waves. And in last year, Jim Peebles and Mayer et al., they were given Nobel Prize again for the studies about the evolution of the universe and about finding the first exoplanet. Yeah, and right now we have in 2020, we have again the astrophysics community is very blessed to get the Nobel Prize and for the understanding of black hole formation as a prediction of general relativity and identifying a very supermassive compact object at the center of our galaxy. So yeah, I would like to brush up your memories with very fundamental concepts. So just as a starting point, I would like to say that I won't be going to any equations or any complicated stuffs here. So this is, even though black holes are very enigmatic stuffs and it involves a lot of general relativistic calculations, we are not going to discuss any of those things here. We'll be sticking to basic equations, basic formalisms that we all know from class 12 and undergrad days. So we all know that Newtonian gravity, which we have studied in high school, that if there are two massive objects, these two massive objects have some force of attraction between them, and this force of attraction is directly proportional to the masses, product of masses, and inversely proportional to the square of distance. So even today, the Newton's idea, which was proposed in 1600, is working very well. We know that even if we are sending some satellite or even if we are studying the dynamics of some planet in some stars, around some stars, so Newton's gravitational theorem, gravitational law is working very well to a very good approximation. Again, we remember from those days that there is some concept called escape velocity. So the escape velocity is the velocity with which we can travel such that we can get out of the gravitational field of a body. So in the case of Earth, this escape velocity is 11.2 kilometer per second. So this is we obtained by equating the kinetic energy and the potential energy. So this is equivalent to saying that the kinetic energy, we can acquire some kinetic energy such that the potential energy of the potential of the gravitational field can be overcome. So another interesting velocity was the orbital velocity. So orbital velocity was the velocity with which the system was, like if there is a sun earth system and the earth is moving around the sun, so the velocity with which this earth is moving around the sun, so that is the orbital velocity. Again, the expression is here, everyone knows these things, I'm not going into the details. So so this was the story of 1600s, but later in 1900, Albert Einstein gave us the theory of relativity. With every one of us know the famous equation E is equal to mc square, which says that mass is equivalent to energy, or energy can be converted to mass, or which gave us all kind of nuclear possibilities and nuclear energy extraction, etc. To say something briefly about special theory of relativity, this is the theory which deals with the frames, which says that okay, irrespective of frames, physics is always the same. So this will give us wonderful concepts, phenomena like time dilation, length contraction, etc. So if you are doing some measurement in one frame, I mean, if you are doing some time measurement in one frame, and if I'm doing the same experiment in a moving frame, the measurement will be different by the with respect to what is the velocity of the frame, etc. So just keeping all those complications apart, we just want to take one information from special relativity, which is the fundamental postulate of special relativity, which says that the maximum velocity with which something can travel is the velocity of light. So that is the maximum attainable velocity for a particle. So we know the velocity of light is the 3 lakh kilometer per second. So that is well known to all of us. So this is the maximum velocity which something can travel. So we know that photons will travel in that velocity, and gravitons and other all massless particles will be traveling in that velocity, but massive particles will be traveling with a velocity less than that velocity. But that is the limit. Now, this when Albert Einstein proposed this idea, so it was working well. It was proved to a very great extent. Then we want all the theories to be compatible with special theory of relativity, because this is a fundamental concept that the frames of reference should be respective, should not matter much in the case of the measurement or in the case of the physics that we are dealing with. So the idea is all the theories that we had known until that day, like electromagnetic theory or gravitational theory. So all these theories should be compatible with special theory of relativity. So it was actually shown that the electromagnetic theory is working well with respect to, or actually the modifications were made, and it was found that okay, electromagnetic theory is working well with special theory of relativity, but Newtonian gravity is not compatible with special theory of relativity. So I will just tell a very simple example, a thought experiment to illustrate that Newtonian gravity is not compatible with special theory of relativity. So I will take you to a thought experiment. So this is like this. So we have the Sun Earth system there, and the Sun is giving the gravitational force, which is actually making, or which is equivalent to the centripetal force, and that will make the Earth rotate around the Sun. So imagine that Sun got disappeared at some point instantaneously. Then the question is, what will happen to the motion of Earth? Obviously, we know that if Sun got disappeared at some point, then there is no source of gravity. So this means that there is no force of attraction or force of gravity, which is making the, which is providing the centripetal force or centripetal acceleration for the Earth. So if there is no centripetal acceleration, what will happen is that the Earth will move tangentially. So second question is, when will the Earth move tangentially? So as per Newtonian gravity, we know that if there is no force of centripetal force, this means that at that very same instant itself, the Earth will move tangentially. So the answer is like this: Sun got disappeared at some point. At that very same instant, the force got stopped, which means that at that same instant, the Earth will move tangentially. Okay, so this is a very instantaneous process as per Newtonian theory of gravity. But we know that as per Albert Einstein, the maximum velocity with which something can travel is the velocity of light. So including the information that, yeah, Sun got disappeared, so that will reach Earth only at a velocity which is maybe equivalent to or less than the velocity of light. So we know if there's something is traveling with a velocity equal to velocity of light from Sun to Earth, it will take at least a time period of 8 minutes. So this is a well-known number to us, 8 minutes. So as per theory of relativity, we can say that okay, once Sun got disappeared at some point, only after 8 minutes, that information, the information of the missing Sun, will reach Earth, and that will make the Earth move tangentially. So there is a delay, or there is a gap between the missing of the Sun and the tangential motion of the Earth. So this is what relativity demands us, but Newtonian theory says that no, this is a very instantaneous process. At the same point, or at the same time point when the Sun disappears, the Earth will move tangentially. So there is actually a conflict. And the question is, who is true? Newtonian theory is working very well, but relativity should also work very well. Then Albert Einstein thought that, okay, Newtonian gravity is not compatible with special theory of relativity. So we need some relativistic theory of gravitation. So we cannot completely say that, okay, Newtonian gravity is wrong. As I have already told, it is working well to a very good approximation. So what we can do is we can just do some kind of modification to Newtonian gravity, and this modification will make the theory compatible with special theory of relativity, but it will also explain all the phenomena, all the processes that Newtonian gravity was actually explaining. Okay, so this is the introduction of general theory of relativity. So general theory of relativity was actually proposed by Albert Einstein in 1915. So this is a relativistic theory of gravitation, and in this, the gravity is not seen as a force. It is not considered as a force, but it is considered as a curvature of space-time. So I don't want you people to get confused. So the story is like this. So we have space and time as a single entity in theory of relativity. So instead of saying that, okay, we have three-dimensional space as a separate entity and time as a separate entity, so we have a four-dimensional space-time with us. So this four-dimensional space-time can be seen or can be considered as a rubber sheet. So this rubber sheet can be seen in the right side of my slide. So you can see that there is a vast spreading rubber sheet of space-time. So for simplicity, it is a two-dimensional rubber sheet because four-dimensional cannot be visualized with our brain. So in this rubber sheet of space-time, there are massive objects like Sun, Earth, Moon, etc. And what will happen is that if there are massive objects, then this rubber sheet will be actually bent, or it will be distorted. So this is like if I'm just keeping a marble on a rubber sheet. So what will happen is that the region around that marble will be a little curved, or it will be bent and that is the geometry because of that. So the geometry of the rubber sheet, which was flat initially, will be distorted because of the presence of this massive object. So this is the picture of gravity in the case of general theory of relativity. Now what will happen? So I have sun here, or let's assume this as earth, and what will happen? There is a curvature around this earth, and if I'm bringing a small stone here near to the that rubber sheet, what will happen is that that small stone or small ball will be actually rolling down towards the center, or rolling down towards the dip of the curvature. So this is actually equivalent to saying that everything is being attracted by that massive object. So now the question is, what will make the curvature? Is it only the massive object that will make the curvature, or is there something else also that can make? So we know that Albert Einstein has already told us that mass is equivalent to energy, or energy is equivalent to mass. So instead of saying mass, it is always better to use energy, which is a general term which includes both relativistic mass as well as the rest mass. So it is always better to say that, okay, if there is some energy, this energy or energy density, which is the exact term, energy density can cause the curvature of space-time around that. Now, why the Earth and Sun is having such a system of Earth is rotating around Sun, or why there is Moon is rotating around Earth? So, what is actually happening there? That is the next question that we are trying to address. So, actually, what happens is that Earth moves in the straightest possible path in the curved background caused by the Sun. So, here I have Sun here and Earth here. So, we can see that because of the presence of Sun, the flat space-time, the flat geometry was actually distorted, or it is bent now. Now Earth is also there, and Earth's presence is distorting the space-time to a little extent, but it is small compared to the distortion created by Sun. Now, because of the presence of this Sun, the space-time is distorted, and the Earth is moving around the Sun. Again, whatever picture of angular momentum, etc., will also come here. So I would like to stress here that Earth moves in the straightest possible path. Why there is straightest possible? Because we know that there is no force of gravity here. As per Newton's first law, if there is no force of gravity, there is no force, external force, this means that the particle will move in the straight line. So if it is moving in some way, then it will continue to move in the straight line. So it won't have any directional change. So there is no force of gravity here. There is no other force here. This means that the particle will move in the straightest possible path. Now the question here is that what is the straight line on a curved surface? So I will come to that, just to say that, okay, if we are just imagining a surface of a sphere, which is the easiest imaginable quantity that we have, which is curved surface. So then how can we draw a straight line? So then the concept of straight line will be changed. I will come to that anyway. So in this slide, I would like to conclude with saying that Einstein equation is the equation here. This is just a blackboard picture that I have taken from somewhere. So mass is the quantity which is here. There are some mu, etc. Don't get confused with those things. Just to understand that this is equivalent to saying that RHS is mass or energy. Then in LHS, this is a quantity called Einstein tensor. That is nothing but which quantifies the curvature of space-time. So this equation says that if there is some energy source, or there is some energy density source, that will result in the curvature of space-time. Okay, so before getting into black hole, etc., I would like to do some fun with curvature. So simply speaking, this is a straight line that I have drawn. So this is a Cartesian coordinate system. Everyone knows these things. I have 2 points here, 2 coordinates here. And what is the distance between these 2 coordinates? This is simply given by this expression. Okay. So this is the case of flat geometry. We simply call it Euclidean geometry. So all the physics, all the mathematics that we have studied in our high school days are valid here. So some of them are like, okay, parallel lines won't meet each other. Some of the triangles, some of the angles of the triangle will sum up to 180. So many such fundamental rules we have studied in the mathematics in our mathematics textbooks of our high school days. So these are all valid in flat space-time. So this is called Euclidean space-time, or Euclidean space. So this is the simple story. Now what will happen if we consider the surface of a sphere? So the surface of a sphere, I have just told you, this is a curved surface. if curvature comes, then the concept of straight line that we had in our mind is not possible, because things are all bent there. Already the space-time itself is curved, and how can we get the straight line? Straight line, in our intuition of straight line, is that there is no change in the direction. That is our basic intuition about a straight line. But here on the surface of a sphere, straight lines are not actually straight lines of our conventional way. Then we define straight line in a different way. But before going to that, I would like to say that, okay, instead of x, y in on the surface of a sphere, we usually use coordinates such as theta and phi. So here, when we say the equivalent expression for the separation between these 2 points, the expression is given by ds square is equal to d theta square plus sine square theta d phi square. Don't worry, this is just an extension of this expression. But I would like to stress here that, so when we write ds square is equal to dx square plus dy square in the case of a flat space, or in the case of a two-dimensional space, actually we can define a matrix called a matrix called metric tensor. So this metric tensor is nothing but the coefficient of this dx dy. So we can see that dx square has, so this is 1 1, so this means that here it is 1. Then here also this is y, so this is dy times dy, so this is also 1. Then we don't have cross terms dx dy, there is no cross term like that, so that is why this is also 0. Now here in the case we have coordinates theta and phi, so this means that here it is 1 and here it is sine square theta. Okay, so this is GAB. So this is, so the point that I want to make here is that always, in order to determine the curvature of a space time, so we can see that this is flat space and here it is a curved space. So what is the difference that we have seen here? So we have seen that, okay, in flat space our metric, or the metrics that I have defined, is having such a form. Here it is having a different form. So which means that GAB is a fundamental quantity which says about how much is the how much curved or how much flat the space time is, or a space is in general. Okay, now I want to add two more things here. As I already told, Euclidean geometry says that, okay, the sum of the angles of a triangle drawn in a flat space is 180 degree. But here in the curved space, this is a simple manifestation. I have drawn a triangle connecting 2 points here, 3 points here. So the straightest possible path that I can draw here between this P and A is going through the longitude. So you are familiar with longitude and latitude. So this is the longitude. So this is the straightest possible path that I can draw between these 2 points. And between A and B, this is the straightest possible path. This is the equator, or then one of the latitude. And this is another longitude. So if I'm connecting these 3 points with the straightest possible path, I can get a triangle. But the fun is like this. So if you measure the angle between these angles of these three, we can find that this is already 180. No? This is already 90 degree. It's very straightforward. This one also will be 90 degree, and this one also will be 90 degree. So if we sum the angles, we will find that this is 90 plus 90 plus 90. This is 270 degree. So the thing is, we have found here the sum as, in the case of flat space, it is 180 degree. But here, just on the surface of a sphere or a ball, we find that, okay, the sum of the angles are not equal to 90 degree. It can be greater than, it's not equal to 180 degree. It can be greater than 180 degree. Another thing is about the parallel lines. So as I've told you, the straight lines are actually which are passing through the longitudes. So I am starting two parallel lines here, two straight lines which are parallel here. In the case of Euclidean geometry, we have found that parallel lines won't meet each other at all. But in the case of a surface of a sphere, we are finding that, okay, we are actually starting as parallel lines, but at the pole, they are meeting each other. So the picture that we have about all these fundamental things, like the sum of angles or parallel lines, these are all going to change if you have curvature with us. So if you have curvature, many new things are coming to us. So curvature is the quantity that is determining actually the gravity. So instead of having all those flat notations, now the space time itself is curved, and that will give us a lot of new additional predictions, new additional quantities that was not there in Newtonian gravity. Now, GAB is the, as I already told, this is it encodes the underlying geometry of space-time. Now, in general relativity, we solve the Einstein equation. This is the Einstein equation to obtain GAB. So GAB is the solution for Einstein equation. Okay, so mathematics is done. Now we want to say that, okay, if we have new theory, this new theory will have a lot of predictions. So some of the predictions are that, okay, light will be bent in the presence of gravity. So we have already seen that, okay, in Newtonian gravity, the gravity is between two massive objects, but we know that light doesn't have have mass. So as per Newtonian gravity, light cannot be affected by any massive object because light doesn't have mass. But here, in the case of general relativity, we are not actually considering between mass interaction. But this is like energy interaction, or in a more general sense, we say that okay, some light is traveling in the straightest possible path here, but if it is traveling in the straightest possible path, actually the space time itself is bent. So what will happen is that when we look at that space time, the light will be seen as bent, even though that is traveling in the straightest possible path given to that. So this is like I have drawn a straightest possible path between A and P, but we can see that on that surface, if you look at that surface, that is not the conventional straight line. So there can be seen some bend. So this is not because of the light or the intrinsic property of light, but this is the intrinsic property of the space-time. So this is one of the important predictions of general relativity, which gave the general relativity some powerful footing. Second thing is that gravity slows time. So if you measure time in a gravitational field, it will be less. So I will come to that later. Third is about black holes. So third major prediction is that, okay, black holes are existing. So I will come to what is called black holes. For these gravitational waves. So gravitational waves are again some predictions of general relativity, which says that, okay, like electromagnetic wave, which is a consequence of electromagnetic theory. Now we have gravitational theory. So gravitational theory will also result in some gravitational waves. So this is like this is actually the traveling of the information that, okay, there is some change in gravity in the field. Okay, so let's come to the idea of black holes. So I would like to take you to the old concept of escape velocity again. So we have seen that, okay, escape velocity is the velocity with which something travels such that that particle can get out of the gravitational field of that system or that massive object. So in the case of Earth, that is 11.2 kilometer per second. But what will happen if some object has a escape velocity greater than the velocity of light? Then nothing can travel from that massive object, right? Because the maximum velocity with which something can travel is the velocity of light. But for this system, for this massive object, the maximum velocity is, so the escape velocity is the velocity of light. So if we combine both these two arguments, we say that, okay, nothing can travel out of that, including light. So this idea was actually proposed long back in 1783. John Michel and even Laplace also had this idea that, okay, what if there is some object which have escape velocity greater than velocity of light? Then they called, okay, there is nothing can travel, even light cannot travel, so we cannot see that object. Then they called those systems as dark stars. Okay, so but those were just proposals. We didn't have enough theory to say that, okay, nothing can travel faster than light. But in 1900, Albert Einstein gave this wonderful theory. So when we combined these, general relativity gave us the idea that, okay, black holes are real and they are existing. So in 1915, just after a few months of the publication of general relativity by Albert Einstein, Carl Schwarzschild in 1916 obtained a black hole solution for Einstein equation immediately after Einstein proposed it. So I told you the Einstein equation solution will be a metric always. So as I have already shown the metric here, in the case of a black hole, the metric will be like this. I don't want to get to those mathematics there. So we will speak about black holes here. So black holes are some spherical systems. They are having some radius. So this radius of the black hole is denoted by Rs, and the surface of the black hole, I mean the region around which region corresponding to Rs is called the event horizon. So what is special about event horizon? So event horizon is the surface beyond which nothing can travel. So once something is get inside the event horizon, then there is no way out. So event horizon is like a one-way membrane. Okay, so the expression for event horizon is given here. So event horizon, anyone can directly derive the expression for event horizon. So it is just equating the escape velocity equation with the velocity of light. So even though general relativistic calculations also give the same result, So this is the expression for event horizon. So event horizon radius. So event horizon radius is proportional to mass. Another important quantity that I want to property that I want to stress here is the center of black hole. So at the center of black hole, what happens is that the whole mass of the black hole is sitting at this center. So at the center, there is actually a singularity. So when we say singularity, singularity is something infinite, something is diverging there. So the density of the black hole is infinite at that. So as I have already told previously, if you have some massive system, and the massive system, okay, mass means there is energy and energy density. So that energy density will distort the space time. But what will happen if that energy density is very large? And if it is infinite, what will happen is that there is like a hole, or there is like a ditch in the space time itself. So this is the point of singularity. So this is the space time of a black hole. So that is actually given by this metric. Now, there are a few important things also that I would like to explain about black holes. So one is that there is a boundary called event horizon. So this is determined by the mass of the object. Now, the most simple thing about black hole is that black holes are the simplest objects in the universe, in the sense that they have only three properties. One is the mass of the black hole. Second one is the angular momentum of the black hole, and third one is the charge of black hole. In astrophysical systems, we haven't yet found any charged black holes, but we have found that black holes are having mass and they have rotation, so they have angular momentum also. Then I have already told about the singularity at the center. Okay, now I will come briefly to some of very interesting things around black hole. So one is like this. So what will happen if some astronaut is there sitting, he is actually in the vicinity of a black hole. So I would like to again give you a thought experiment. So before that, this is a scene taken from the Interstellar movie. So they says that 1 hour in this planet, or on this planet, is 7 years on Earth. So this idea might be familiar to many of you, that okay, near a very massive object, the flow of time, or the speed of time, slows down. So which says that if it is 1 hour there, that will be equivalent to 7 years, or that will be equivalent to 100 years. So this kind of time dilation is solely a general relativistic effect, and around the black hole also that can be seen. So I would like to give you again another thought experiment. So it is like this, and just before that, let me just consider one astronaut traveling from a spaceship. So this spaceship is actually near to a black hole, but it is not very close to a black hole. So let's say that, okay, it is 100 kilometers away from a black hole. So this spaceship is halted there. So there are many astronauts sitting in that spaceship. And one of the astronaut is actually moving towards the black hole radially. So the story is like this. This story was told by Stephen Hawking only. Again, many people have visualized this. So this is one of the easiest way to visualize time dilation. So the moving astronaut. So I have told you the one of the astronauts is actually moving towards the black hole radially. So this astronaut is he has actually agreed with his fellow companions that okay, in a time interval of 5 seconds, I will send a pulse to you people. So I will always send in a time interval of 5 seconds, I will always send some pulse. So that will be anyway received by the people in the spaceship. So just to make sure that okay, he is alive and he is not dead, or yeah, just some kind of agreement. So yeah, things are smooth. Like he has started traveling towards the black hole. So in 5 second interval, he is sending the pulse, and in the 5 second interval, the other people will be receiving. Now, what will happen is that this guy is moving towards the black hole. Then this time dilation thing happens. So the moving astronaut, let us call him Alice. So this moving Alice, he is sending the pulses within a time interval of 5 seconds in his clock or in his watch. But as he is moving towards the black hole, the people who are sitting there will find some kind of time dilation. Even though Alice is sending with a time interval of 5 seconds, Bob, who is sitting in the spacecraft, will be receiving it at a little larger time interval, let's say 10 seconds. Now, after something, what will happen is that this 5 seconds, so Alice is always sticking to the agreement. He is always setting it at 5 seconds, but the reception time interval is now increasing. So 5 second here will be 10 second there. After some it is 5 second here will be 20 second there. Then it is 5 second. It is 1 hour there. So in that way, it is actually increasing, increasing, increasing. Now, what will happen when he is getting close to the event horizon? So when he is getting close to the event horizon, uh, the Alice is sending actually within 5 seconds, but Bob will not be receiving that at all. So this will be like this. So Alice is again sending at 5 seconds. After some time, this is Bob will be receiving at say 1 day. That kind of expansion happened. Now what will happen is that again Alice is actually moving towards the event horizon. Alice is sending at 5 seconds. Then when he touches the event horizon, nothing can come out of that, right? Even the light pulse won't come out of that. Then what will Bob think? Bob will be thinking that, okay, this guy is not sending, or he might be sending, or his time may not be moving at all. So some kind of time stopping happens if Alice is at the event horizon. Now what will happen? This Alice is moving again towards the event horizon. I mean, towards the singularity, or towards the radially inside the black hole. Then there is no way for Alice to send, because whatever inside the event horizon, whatever inside this black region won't be coming out of that. So Bob is not going to receive any signal once Alice enters the event horizon. So this time dilation phenomena is explained by this expression. So this is one interesting thing that can be seen around black hole. So in the Interstellar movie also we can see that Cooper was actually traveling traveling to a planet which is close to the gigantic black hole. So it was again time dilation happening there if we compare it with the time in Earth or in other spaceship. Second thing is about spaghettification. Spaghettification is nothing but a very simple phenomena that even happens in Earth. So let's assume that there are 4 points or 4 points which are actually falling towards Earth. So they are actually falling at a circle. Okay. Now what will happen is that after some time, these 2 points, their separation will increase, and these 2 points, their separation will decrease. This effect is called tidal effect. So this tidal effect is even present in Earth or in Moon or in any gravitational system. So this is because of the fact that gravity is not uniform. We know that gravity is a function of r, or the distance from the center. So this is the effect of tidal. So this is actually causing even the tidal effects in oceans and sea. So which is because of the tidal effects between moon, sun, earth, etc. So what will happen in black holes? So even though spaghettification or tidal effect is there in Earth, sun system, etc., the effect is very small there, because we can say that the gravity effect in Earth, Moon, Sun, they are very small. But in the case of black hole, the gravity is very large. The density is very large. Because of that, the variation of gravity at each inches or at each centimeters will be very high, and that will cause a spaghettification of very large extent. So as an astronaut is falling, what will happen is that he will be squeezed. So this means that his height, I mean, at the horizontal level, sorry, at the vertical level, he will be elongated, and in the horizontal level, he will be compressed. So after some time, even he will be actually destroyed. He will be powdered to simple atoms or even quarks. So this is spaghettification is another interesting aspect around black hole. Okay. So these are some interesting things about black holes. Now we have to say about how black holes are actually formed in the universe. So very easy way to say is that okay, we have stars which are fueled by the nuclear fusion. So once the fuel in the sun or other stars got exhausted, then they will undergo gravitational collapse. So once the gravitational collapse starts, and given the initial mass of the imploding stars, then the end state can be different. So either the imploding star will lead to a white dwarf, or it can lead to a neutron star, or it can lead to a black hole. So there are actually three end phases for a dead star. One is a black hole, or it can be a white dwarf, or it can be a neutron star. So yeah, actually this slide is taken from Bani Prato's lecture last week. So again, what is the determining factor that will result in a black hole or a white dwarf or a neutron star? So that is the initial stellar mass. So if the stellar mass, which is resulting in this collapse, is less than 8 solar mass, it will result in a white dwarf. Or if it is, okay, just to mention, this m solar is the mass of sun. So usually in astrophysics, we speak mass in terms of the mass of the sun. So neutron star is second quantity, second depth phase. So if the stellar mass is between 8 solar mass and 15 solar mass, it will result in neutron star. Then black holes, if it is having a mass greater than 15 solar mass. So in the case of our sun, if the collapse happens, it will eventually become a white dwarf. That is clear from here. So yeah, if black holes are there, so one of the death phase is black hole. I don't want to explain wide dwarf or neutron star here, given the time limit. So black holes are there, which are one of the death phase. So black holes can be stellar mass black holes or supermassive black holes. So stellar mass black holes are having a mass of the order of 2.8 solar mass to 90 solar mass. I'm just giving you some numbers to give that intuition that, okay, how much massive is these things. So supermassive black holes are the black holes having million times solar mass to billion times solar mass. So the mass difference is actually very huge. So another important picture is that, okay, sun is there, white dwarf is there, neutron star is there, black hole is there. So this is the space time around that. So as the density of the system is increasing, then the curvature of space time around it will also increase. So sun doesn't have much density comparing to white dwarf. Neutron star has more density comparing to white dwarf. Black hole has infinite density. So you can see that effect in the curvature also. Okay, whatever I have explained is again in this flow, in this picture. So given the small star, it will actually result in a white dwarf. Or if it is a large star, it will result in a supernovae, and one of the remnant can be a neutron star or it can be a black hole. Okay, so what was actually done by Roger Penrose, and what actually gave them the Nobel Prize for Roger Penrose? That is the question that I would like to address here. So in 1965, Roger Penrose showed that black hole singularity cannot be avoided when matter collapses due to gravity. So in physics, if there is some infinity, so you all are aware of that. So infinity is something which says that, okay, we don't have any information about that, or it says that, okay, our theory is diverging there, so it is a meaningless thing. So if there is some infinity, so in most of the cases it will be because of the some mathematical issues that we have, or maybe the theory may not be right or something. So in singularity or infinity is not something real, so it is not easy to say that, okay, there is something diverging there in real. So even Carl Schwarzschild, okay, I'll just go to that slide. Okay, so when Schwarzschild, when he proposed this metric for a black hole, so he found that if at r equal to rs or r equal to 0, so at r equal to rs, you can see this quantity will be 0 and this quantity will be infinity. And at r equal to 0, we can see that this quantity will be infinity. So infinities are coming at two particular radius, at r equal to rs and at r equal to 0. So people were confused, like, okay, why there is an infinity coming at these two radius? What is special about that two radius? And later people have found that at r equal to rs, which is the radius of the event horizon, people have found that there is no singularity at all. That is some effect of the coordinate system that we have chosen. So if we choose some other coordinate system, we can avoid that singularity. So that singularity is called a coordinate singularity. But at r equal to 0, there is no way to remove that singularity. So if you calculate, if you are a little mathematically aware, if you calculate the Riemann tensor of the space-time around a black hole, then we can see that, okay, even at the Riemann tensor level, there is singularity present. So this means that this is not any mathematical issue, or this is actually a real thing. But again, Einstein, etc., were skeptic about this. So it was like a confusion why there is a singularity. But in 1965, Roger Penrose, he used topological quantities, topological and mathematical tools. He was a mathematician also. He used some concept of mathematics to show that, okay, singularity is not an avoidable thing. It cannot be avoided, and it is a real thing when matter collapses due to gravity. So again, I'm not an expert about the mathematical details, and also I don't want to explain those things even through reading. So I just want to say that, okay, in this figure, so this is the figure given by Penrose itself in original paper, and even Nobel Committee has given it in their website. So we can see that singularity is here at the center, and this red surface is the event horizon. So this is a cross section of the black hole. So there are some concepts, if you people are aware about special relativity. So we have light cones. So if you draw light cones at different points around and inside the event horizon of a black hole, we can see that at the center of black hole, light cones will always be directed towards the singularity. So this means that we have past light cone and future light cone. So the future light cone is the so only the things will be traveling through the future light cone or in the boundary of the light cone. So we can see that, I mean, even at the even if I draw a light cone at the event horizon, so this event horizon is a red line, we can see that all the future light cones are directed towards the center of the black hole. So there is no path or there is no way outside the event horizon. So which means that, okay, everything will be coming towards that. Again, if you draw inside, if you draw a light cone inside, again, we can see that, okay, the light cones are all directed towards the singularity itself. So singularity is this blue line, which is r equal to 0 value. So again, this is a space-time diagram, and y direction is the time and x direction is the space. Okay, so this is one of the major major study that Roger Penrose has done. And then we have another important thing, I haven't written it here. This is like event horizon is existing around this singularity. So this means that even though there is a divergence in theory, there is a real singularity existing at the center of a black hole, we cannot see that. So because no information is coming out of black hole, right? We can see only the up to the just a little above the event horizon. So which means that event horizon is blocking or it is covering the singularity. So even Stephen Hawking, etc., they actually worked on these things and they found that there is no naked singularity. If there is a singularity in the universe, then that singularity will be covered by some way. So we cannot access that diverging information or that divergence of theory we cannot see actually. Okay, I just want to say that, okay, the motivation of all this work was from some works done by one of an Indian physicist called A.K. Rai Chowdhury, who was a lecturer at Presidency College in Kolkata. So people, Hawking and Penrose, they have used the famous Raj Chowdhury equation. Now, okay, so we are coming to the last part. So the question is, how can we know the existence of black holes? So black hole cannot be seen. We have already seen that black holes are not emitting anything. So we cannot see black holes directly, but we can see their effects, and that effects can be studied and we can use them to understand the physics and properties of black holes. So one of the first indirect observation of black hole was quasars. So quasars are very interesting astrophysical objects. So quasars are the most luminous objects in the universe. So these objects, so we know that galaxies are there, and galaxies, in a typical galaxy, there are around 10 to the power 11 stars. So if we combine the whole stars, so there will be an equivalent brightness, right? So quasars are actually a single object which have brightness greater than the whole brightness of a galaxy. So these are the brightest object in the sky, quasars, and these are very enigmatic, very interesting stuffs. So we understood that in 1963, Schmidt found quasars, and he has observed some radio jets coming out of quasars. So when I say radio jets, so radio jets you can see in the right side. So these are actually relativistic beaming of fast moving electrons, protons, and other charged particles from the center of this galaxy or from the center of this quasar. And this is extended to very distant regions, say kiloparsec. So these are radio jet, and calculations shown that to have the luminosity of this much amount, there should be some kind of massive black hole sitting at the center of this. So this is a very schematic diagram of a quasar. So later people have found very many varieties of quasar-like things. So we have blazars, we have Seyfert galaxies, and all these family of things are enigmatic stuffs are currently called AGN or active galactic nuclei. So these AGN, so this is a schematic diagram of an AGN. So we can see that at the center, there is a black hole sitting. So black hole is not actually visible here, but you can see the pointer. And there is an accretion disk around this. And there are astrophysical jets moving out of that. So from the observation, we found that in order to have this much luminosity, there must be a black hole sitting at the center, and this black hole is responsible for the astrophysical jets as well as the luminous objects like quasars. So the mass of the black holes were also estimated, and they found that this is not like some 10 solar mass or 20 solar mass, but these are million solar mass to billion solar mass. So such black holes are called supermassive black holes. Now, second major observation is X-ray emission during the accretion in binary systems. So this is the image. So we know that 90% of stars in the universe, they are actually binary. Maybe 90 is a rough estimate. Okay, we can say most of the stars. That is the best way to say. So most of the stars in the universe, they are actually in binary. Binary means that they are not single stars. There will be two stars combined and they will be rotating in the common center of mass. So in one of the binary system could be a black hole, because if star get out of fuel, then it can become supernovae, then it can become a black hole. So even after the formation of black hole, the system will be in binary only. So one of the companion can be binary. So one of the companion of the binary, one of the partner of the binary is a black hole. What will happen is that this black hole will attract masses, gas, etc. from the companion star. So this, you can see that this is a star and this is a central black hole. So because of the attraction or because of that engulfing or eating of masses from the companion star, what will happen is that that will result in some kind of accretion disk forming around the black hole, and that will result in a lot of emissions. So that is our point. There can be emissions in various bands, including X-ray. X-ray is the major emission at that point. So that also have been observed, and all these observations will tell us what is the spin of the black hole and what is the mass of the black hole. Third one is major one is a supermassive black hole at the galactic center. So that is the Nobel winning result, and I will come to that in the next slide. Then we have gravitational waves coming from black hole systems. So the image is shown here. So if you have again two binary black holes, so like two binary stars, so there can be binary black holes. So these black holes will be rotating around each other as shown here. So just to be cautious, these are actually white because just to see, black holes will be not white, they will be black only. So they are actually rotating around the common center of mass, and these are very massive systems. So when there are rotations or astrophysical processes which involves change in mass, that will result in gravitational waves. So you can see that gravitational waves are emitting. So this is like, so gravitational waves are actually waves that we see in water. So ripples in water. So if you just drop a stone in water surface, then we can see that waves are traveling in the water surface. So this is something like that, but here instead of water surface, the ripples or the perturbation or the waves are in the curvature of space-time. I don't want to get into the details, but gravitational waves have been observed by LIGO in from 2017, and LIGO has been operational for the last 5 to 6 years, and they have observed nearly 50 set of black hole neutron star emissions, and it is actually a new window to studying astrophysics, because in most of the binary black hole systems we don't get any electromagnetic radiation, only we can expect black holes. So yeah, gravitational waves from black hole system is one of the way to study black holes. Then we have very recent direct imaging of photon orbits around black holes. So this is the picture. So you might have seen this beautiful image 2 years back. Event Horizon Telescope collaboration, they have taken the photograph of black hole. So what happens is that some noise. Can anyone unmute them?
Yeah, a girl has just unmuted. I have muted her. You can continue, Fazlo.
So yeah, so this is the EHT collaboration image of a black hole. Again, if you take the image of a black hole, we have to understand that black holes are not emitting. We cannot see black hole. We will be seeing some kind of silhouette. So black hole will be there at the center, and black hole will be blocking other things from coming. So the central black thing is the black hole, and we can see photon trajectories around that. So this Event Horizon Telescope team. So this is actually a set of telescopes set up at different parts of the globe, and all the images are actually combined to form a beautiful image of black hole. So yeah, again, I'm not giving any of the further details given the constraints of time, and if you have any doubts, you can ask later. So these are the major observational evidence that we have about black holes. So yeah, we'll come to the work of Andrea Ghez and Renard Genzel. So they were actually two independent group. Gaze was in UCLA and Genzel was in MPE. So yeah, they were actually tracking stars at the center of Milky Way. So what they have found is that uh, these many of the stars, they were actually following some orbits around a particular center. So if we actually from the basic Kepler's law, we can, if we can track the velocity of some orbit, if we can measure the orbital velocity, and if we know the radius, then we can actually infer the mass of the central object, right? So this can be applied to many systems like planet mass measurement, or in many cases. So same thing was actually done by Andrea Ghez and Genzel. So they were observing stars at the center of our galaxy. So you can see many stars, S12, S1, S2, S14. So actually this region is near to Sagittarius constellation that we see from our sky. So they have found that some of the stars like this S2 star, so they have done the observation for nearly 16 years. So they found that S2 star is actually completing its orbit in this 16 years. And they have also obtained orbits, not even though a complete orbit, not a complete orbit. They have got some incomplete orbits for other stars. And what they have found is that from all these observation, from tracking the velocity of all these stars, they have found that the mass of the central object is very large. So they have found, they have measured the value to be 4 into 10 to the power 6 solar mass. So this is like 4 million solar mass. So something at the center which is having 4 million solar mass, it cannot be a star, or it cannot be a neutron star, or it cannot be a white dwarf, because the gravitational effect or the gravitational strength of that system is very large. So it will be collapsing gravitationally, and the final entity will always be a black hole. So from this, we have inferred that, so these two independent groups, they have inferred that, okay, the central object around which all these stars are rotating is a supermassive black hole, and the mass is actually given by 4 million times solar mass. So I have a beautiful simulation that they have made. Actually, this is not a simulation, this is the actual observation only, but a computer animation of that. So you can see that many stars are moving randomly. So this is actually not random, they are actually rotating around this central object. Sorry, I should go out. Yeah, I'll play it again. We can see that many stars are moving. So I have a star mark here. So this is the region. So actually near to this region, somewhere here is the central black hole sitting. So this yellow one within these 16 years, so you can see this is actually starting from 1995 to, okay, this is nearly 20 years, 21 years. So within this time, many of the stars are moving, but this S2 star, S02 star is actually completing a rotation. So S02 star is found to have an orbital period of 16 years. So we can see that all these stars are moving around and around a massive object, which is a supermassive black hole. So this was actually the work done by these two collaborators, and they were given the Nobel Prize for this work. Again, what is so special about it? So this is not very easy thing to do, because the central region of our galaxy, it is not easy to get optical light from there, because there are a lot of dust emissions from there. So the observations were done in infrared telescope, in Keck telescope and VLA, I think, if I remember correctly. So they have done a very Herculean task. They have achieved this, and they have found that, okay, the central massive object is a black hole. So this is like in our courtyard, like in our own galaxy, there is a black hole sitting, and that black hole is, so this will be our nearest black hole. So we don't have, so yeah, so we haven't, if I remember correctly, we haven't found any other black hole near to us. So yeah, I think I'm almost done with the discussion. So in the last part, I will discuss some of the work that we have done during my master days on the formation of supermassive black hole. So as I have already told, all the discussions about black hole formation was in the context that, okay, stars were actually having death phase, and that will result in black hole. But star death phase black holes will have at max 90 solar mass. Supermassive black holes are another class of black holes which cannot be formed as a collapse of stars or a death phase of stars. So then the question is how supermassive black holes are formed. Supermassive black hole formation is a very enigmatic. It's a very big puzzle still in cosmology and structure formation. So the problem is like this. We can think like this, like there are many black holes, small black holes. They will combine to form big black hole. They will aggregate to form big black hole of this mass. So that is a possibility that we can actually think of. But the problem is that this will take a lot of time. So this is not easy like, okay, everyone is coming at some point and just hitting. So there will be a lot of dynamics involved and we can calculate the time. So this time is very large. So supermassive black holes, we have observed that they are there in the very early phase of the evolution of the universe. So just after 1 billion year after the evolution, after the Big Bang, we can calculate the age of the supermassive black holes. So they are very old stars, sorry, old black holes. So the question is how this much massive objects, massive supermassive black holes are there in the very early days. So this was the problem that we were addressing. So during my master days, I worked with Patrick from Delhi University. So we proposed an idea that okay, there is dark matter in the universe, and this dark matter can be, there is a proposal that it can be made of ultralight particles like axions, etc. And these are actually quantum mechanical particles. So if we introduce quantum mechanics, then we have additional quantum pressure like uncertainty pressure, which can gravitationally collapse to form supermassive black holes of this much mass, 10 to the power 9 solar mass. So we found that we actually calculated, okay, within this small time scale, supermassive black holes of having, I mean, if I say Kerr, I mean, supermassive black holes having angular momentum is formed. So we also have calculated the time scale of collapse, and we calculated the amount of gravitational waves emitted during this collapse. And this can also give some constraints on the mass of the individual particles like axions that make up the dark matter. So yeah, this work is actually still not complete. We will be coming to this after some time. So the incomplete archive version is available. So Patrick is here. So he is still there in Department of Physics at Delhi University. He is currently the head of the department. So yeah, I think I'm almost done. Thank you.
Thank you, Faslu. Thank you for your wonderful talk. Now, I think you will be able to share a few more minutes if there are any queries that are to
Yes,
be
yes,
addressed, I
I'll
think.
be, yes, I'll be happy to do that. Can I
I
see the
have a
chat?
query. I'm not sure whether you are looking into it or not during your research work. It is about the various thermophysical processes that may be occurring inside a black hole. As the temperature is supposed to be very large, there are scope for different kind of statistical processes. I'm not
Mhm.
sure whether you are looking into it or not, because your work is basically concentrated on some experimental procedures.
Mhm. Are you asking about my current work or this work about the supermassive black holes? Hello.
Yeah. Pardon me. I was
Yeah.
not able to get you.
It's fine. Is it about this work on supermassive black holes you were asking in the context of that?
No. Actually, about the various possibilities of thermophysical processes
Yes,
that,
yes.
yeah, inside a black hole.
Mm-hmm. Yeah. As far as I understand, so these are actually done as the thermodynamical system. So actually, black holes are thermodynamical systems. So when we include quantum mechanical effects, so whatever I have explained here is completely classical in nature. So if you bring quantum mechanics to here, I mean, just put up the quantum fields in these general relativistic space times. So then we can see that okay, there are thermodynamical effects coming, such as the evaporation of black holes, and we can get a temperature to that black hole, and we can also say that okay, the area of a black hole, I mean the area of a given horizon is equivalent to saying that okay, that is the entropy of a black hole. So in any thermodynamical system, any thermodynamical process, the entropy will be always increasing. So this is equivalent to saying that if you have two black holes and if these two black holes are combining, then the energy of the entropy of the sum of the black holes, or the entropy of the final black hole, will be always greater than the initial black hole. So I think people have actually done that. Again, I have not done all those things. Yeah.
Yeah, yeah. Okay, thank you. And I have asked them to put their queries on the chat box. No queries has yet
Okay.
come.
Okay.
Yeah, and I know that you have to
Hi.
attend one more meeting very shortly.
Okay.
Faslu.
Yeah, Basim sir is on the
Hi.
line.
Yeah,
Yeah.
I'm asking. So, what
Mhm.
influence they have the black holes have on our planet? The supermassive black hole in our galaxy center. So, what do they have any influence on our planet?
You mean our solar system, right? In our planet.
Yeah,
So far, we don't
yeah.
have anything because we are actually very far away from that. And
Okay.
again, if we check the mass of the black hole and the mass of the total galaxy, so the presence of a supermassive black hole is not determining much about the gravitational center or gravitational barrier center. So we know that stars and all, including solar, our sun, they are actually moving around the common center of mass, right? So my point is that even though the presence of black hole may shift the barrier center, but it is not very large because our distance to the center of galaxy is 8 kiloparsecs. That is very large. So I don't think that there is a very huge impact on that. Maybe there can be a very small effect because of the presence or absence. So if you don't consider this contribution of supermassive black hole into the total mass of the galaxy, which will determine the dynamics of our sun or I mean our motion in the galaxy. There could be some very small effect, but it is very tiny. It's not going because the mass of the galaxy is 10 to the power 11 or 10 to the power 12, if I remember correctly. This is 10 to the power 6. So it's 6 times order of magnitude. So it is very less.
Yeah, Faslu, there are a few queries in the chat box. Sir, how those jets origin from black hole and how they are escaping from black hole gravity is raised by a acidic ball. And one more query is there, how is it possible to track a star in the center of a galaxy?
Okay. So I'll answer the first question. So this is about relativistic jets. So this is actually a very complicated process. So as I've told you, so there is a black hole, and this black hole will actually attract things from outside. So there will be many things coming into the galaxy, like there will be dust particles, there will be gas, etc. So these systems will not directly fall into the black hole, but what will happen is that they will actually form an accretion disk around it. So, accretion disk, what I mean is that this is a disk composed of gas and dust. So they are not directly falling into the black hole because whenever something is coming, that thing will have some kind of angular momentum. So in order to conserve the angular momentum, it cannot directly fall into the black hole. So what will happen is that they will have an accretion disk around that. So you can see the accretion disk is always, oh, I cannot see my pointer. Yeah. So accretion disk is it's the bright region around the central black hole. So from the accretion disk, actually the dust and gas particle will slowly fall into the black hole. Again, when they fall into the black hole, we have to conserve angular momentum and many other physical mechanisms. So this will result, in order to conserve angular momentum, etc., this will result in the emission of various radiations, and also this will heat up the system. The presence of radiation will heat up the system. So when we say that, okay, there are dust particles, there are gas, and there will be, and the system temperature will be very high, such that many of the things will be in plasma, they won't be in neutral. So there are fast moving electrons, there will be fast moving protons, etc. So it's a very complicated system, and because of that, again, other thing is that this black hole will give energy because of this accretion as well as falling into the black hole. So because of this, there will be jets coming out of these black holes. So as I've told you, black hole jets are actually fast moving electrons and protons. So again, the presence of jet and the position of jet will be aligned with the spin of the rotation. So black holes are rotating, so they will have a particular direction of rotation, right? So the jets will be always aligned in the direction of the rotation or direction of the spin. So these are very complicated thing, but still, yeah, people have actually calculated how this is done, so we can find that jets will be there. Second thing is that how jets are emitted from black hole. Jets are not emitted from black hole. Jets are actually coming from the accretion disk around the black hole. So nothing can come out of black hole. Even the question is can be asked here, how gravitational waves are coming inside from a black hole. Again, this is not coming from the inside of a black hole. It is coming from the region of the black hole where black holes are there. So there can be anything coming from the inside of a black hole, including this image. So we have to keep that in mind. I hope I have answered that. What is the second question? How is okay to track the
Track the star at the center of the galaxy.
yeah. So velocity measurement, that is what we are doing, right? We can see the stars, then we have to get the velocity, I mean the radial velocity. So velocity measurement is actually, in most of the case, a radial velocity measurement is done by looking at the Doppler shift in the spectral lines that we see. So it will be either, if it is coming towards us, it will be blue shifted, or if it is moving away from us, it will be red shifted. And from the shift, we can calculate the amount, I mean the magnitude of the velocity. So that is the way it is done. So as I've already told you, once we get the velocity, we can get the mass. But calculating the velocity is a very complicated process. So there is actually a plot here which gives the radial velocity with respect to year. So this is for S2, I mean S2 star. But the challenge is that the flickering of the star will actually give us some kind of noise or some kind of error in the measurement. So people have used some techniques called adaptive optics. So you can just Google and read it up. It's a very interesting technique that is recently introduced and that is used widely in astrophysics these days. So adaptive optics technique is used to address the atmospheric effect, I mean the twinkling of stars, which can cause some error in the measurement of the velocity. So they have done a very difficult task, but finally they have achieved it. So yeah. Any other question?
Yeah, there is an interesting question that whether a black hole can explode. I think Farsina raised it.
Whether a black hole can be exploded. Black hole,
It's
actually
not
black,
expected. As always, it will have an implosion.
yeah.
Black holes will always have an implosive effect. That is
Uh-huh.
entirely different from the normal explosion that we will be
Yeah,
facing.
yeah.
Yeah.
I was thinking like what will happen if it is like two black holes and they will merge. So can it be seen as some kind of explosion? Again, it is not an explosion; it's a merging only. Yeah, fine. If there are black holes in space, would they affect views of stars in the background? Of course, yeah, yeah. So that is what is we have seen here, right, in the event horizon image. So once black holes are there, they will block. Again, black holes, there is another effect which I have missed, that there is some lensing of image by black hole. So black hole is sitting at the center and there is some galaxy or some star behind the black holes. And because of the presence of this massive black hole in the view or in the path, the light will be bent. So we can see multiple images of that same star. So this is called gravitational lensing. So these are actually important tools that we use in astrophysics to study black holes. Actually, I have missed to say that. Yeah. So I don't find any other question.
Yeah. I think it's almost done, and there is a comment by Shafi sir. He's appreciating you, Fazlu, and we are also take this opportunity to appreciate you. Go on with your work. Try for the Curie Fellowship next time, and in the meanwhile, try to have a few wonderful, say, papers also.
Sure. I can see one more question here. Shall I answer that? Faiz PK, won't there be gravitational waves from binary star systems? Yeah, it can be there, but the small. So stars will have actually stars are very simple systems, right? So the amount of gravitational waves will be very less. and it cannot be detected. Even black hole gravitational waves are very difficult to detect, but it is black holes that is why we are detecting that. I think we can conclude with this. Okay, I have my email ID in the last slide. You can write it. You can write to me anytime. I will reply you.
Oh, you have changed it. Yeah, it is your institution email ID, I
Yes,
think.
yes. I actually use
Earlier it was Faslu Bismi, something like that.
yeah, right. I
Yeah.
cannot use it like
And Basim sir, you have something to tell?
No, no, no. So now we can conclude.
yeah. So I'm
Yeah.
really thankful to you all for this wonderful opportunity.
Okay.
Now let me invite somebody from the class to conclude and to propose the vote of thanks. Asna, can you hear me?
Yes.
Yeah, Asna, please conclude. And I will call Nandana Shekhar for the vote of thanks also immediately after Asna. Asna, please.
Hello.
Yeah, you
Hello.
are audible. You can. Yeah, you are audible. Start talking.
So, നമുക്കെല്ലാവർക്കും ഒരു ഡീപ്പായിട്ട് അത്ര ക്ലിയർ അല്ലാത്തൊരു ടോപ്പിക്കായിരുന്നു ബ്ലാക്ക് ഹോൾ. സാർ ഇത്രക്കും കുറഞ്ഞ സമയത്തിൻ്റെ ഉള്ളിൽ തന്നെ ഇത്രയും ഡീപ്പായി പറഞ്ഞതിന് താങ്ക്സ് ഉണ്ട്. പിന്നെ ഈ വെബിനാറിനെ കുറിച്ച് പറയുകയാണെങ്കിൽ ഫസ്റ്റ് റിലേറ്റിവിറ്റി പറഞ്ഞത് മുതൽ ഹലോ
Yes, we can hear you.
You are audible. Continue. Asna, you just continue. Don't jerk your microphone. You just continue. You are audible. I think she lost the connection. Now let me call Nandana. Nandana Shekhar, you hear me?
Hello. Sorry, I can hear.
Yeah, please. Yeah. Please make your comments and
Okay,
propose a vote of thanks. Yeah.
sure, sir. Very respected teachers and Fazlur Rahman sir, on behalf of my classmates and my class, it's my pleasure to propose the vote of thanks. We want to express our gratitude to you, sir. It was a great session. Thank you for sparing your precious time for us and graces this webinar. It was a really great session, sir. I would love to have another one. Sir?
Yeah, thank you, Nandana, and thank you once again, Fazlu. Yeah. Thank you, Nandana. You can mute, and that is the end of this webinar. Thank you, Fazlu, once again on behalf of the entire faculty community of the department, and keep going and keep in touch.
Sure, sure.
Take care. Bye. Now you can leave. I'll be stopping the recording.